There is something deeply unsettling about the idea that anything in the universe could be truly permanent. Humans have long sought permanence in monuments, in legacies, in the stars themselves. And for much of the history of science, black holes seem to offer at least the theoretical possibility of something eternal. They were the ultimate cosmic fortresses, regions of space-time so warped by gravity that nothing, not even light, could escape their grasp. Once something fell in, it was gone, forever. The laws of physics as understood through Einstein's general theory of relativity seemed to demand their immortality. A black hole once formed would simply sit in space, accumulating mass when matter fell into it, growing ever larger but never dying. It was a seductive and terrifying image. The universe's ultimate survivors, outlasting stars, galaxies, and perhaps everything else. But then Stephen Hawking changed everything. In 1974, Hawking published a paper that stunned the physics community. Drawing on a synthesis of quantum mechanics, thermodynamics, and general relativity, three pillars of modern physics that rarely play nicely together, he demonstrated that black holes are not truly black. They glow, they radiate, they slowly, agonizingly slowly lose mass. And given enough time, almost incomprehensibly vast amounts of time, they will completely evaporate, disappearing in a final burst of energy, leaving nothing behind. The permanence of black holes, it turned out, was an illusion born of our ignorance of quantum mechanics applied to curved space-time. The universe does not permit true immortality, not even for its most fearsome gravitational monsters. To understand why black holes cannot last forever, we need to take a long journey through some of the most profound ideas in all of physics. We need to understand what a black hole actually is, how gravity warps space and time, what quantum mechanics says about the nature of emptiness, how thermodynamics governs even the cosmos, and how all of these threads weave together into the astonishing conclusion that every black hole is doomed. Not quickly. For most black holes, the timescales involved make the current age of the universe look like the blink of an eye, but inevitably and absolutely. The universe is patient, but it is not merciful even to black holes. Let us begin at the beginning with gravity itself. Gravity is the oldest force known to humanity. Long before anyone understood electromagnetism or the nuclear forces, people felt the pull of the earth and watched the moon circle overhead and observed the planets wander among the stars. Newton gave us the first mathematical framework for understanding gravity in the 17th century. Every mass attracts every other mass, with a force that grows stronger as masses increase and weaker as distance increases. Newton's gravity was invisible, instantaneous, and absolute. It acted across empty space without any medium or mechanism, a fact that troubled Newton himself, who found it philosophically unsatisfying even as he used it to spectacular effect. For over 2 centuries, Newton's theory of gravity served science extraordinarily well. It explained the motion of the moon, the tides, the orbits of the planets, the trajectories of comets. It was used to predict the existence of Neptune before anyone had seen it, simply by noticing anomalies in Uranus's orbit and calculating where a hidden planet would have to be to cause them. But cracks began to appear. The orbit of Mercury did not quite match Newton's predictions, and more fundamentally, Newton's gravity was incompatible with the revolutionary ideas Einstein was developing about the nature of space, time, and light. Einstein's special theory of relativity, published in 1905, demolished the old Newtonian framework in which space and time were absolute, fixed backdrops against which physical events unfolded. Instead, Einstein showed that space and time are intimately linked into a single 4-dimensional fabric called space-time, and that the measurements of space and time made by different observers depend on their relative motion. Nothing can travel faster than light, and this speed limit is absolute, woven into the structure of space-time itself. Newton's gravity, which acted instantaneously across any distance, could not be reconciled with this picture. 10 years later, in 1915, Einstein completed his general theory of relativity, and it was one of the greatest intellectual achievements in human history. In this theory, gravity is not a force at all in the traditional sense. Instead, it is a consequence of the curvature of space-time. Mass and energy warp the fabric of space-time, bending and distorting it, and other objects move through that curved space-time along the straightest possible paths. What we perceive as the gravitational force is actually the effect of this curvature on motion. The Earth curves space-time around it, and the Moon follows the straightest possible path through that curved space-time, which turns out to be an orbit. The Sun's gravity is really the Sun's warping of space-time, and the planets orbit because they are following the natural contours of that warped geometry. This is a breathtakingly beautiful idea, and it is also extraordinarily precise. General relativity correctly predicts the precession of Mercury's orbit that Newton's theory got wrong. It predicts that light bends as it passes near massive objects, confirmed dramatically during the solar eclipse of 1919. Which made Einstein world-famous overnight. It predicts gravitational time dilation, the slowing of clocks in stronger gravitational fields. A real effect that must be accounted for in GPS satellites, which otherwise would accumulate position errors of kilometers per day. It predicts gravitational waves, ripples in space-time caused by accelerating masses, first directly detected in 2015 when the LIGO observatories heard the collision of 2 black holes a billion light-years away. General relativity has passed every experimental test we have subjected it to. with extraordinary precision, and it remains our best theory of gravity more than a century after Einstein published it. Within weeks of Einstein publishing his field equations, the German physicist Karl Schwarzschild found the first exact solution. He was working on the Eastern Front during the First World War, doing physics in the trenches, and he solved Einstein's equations for the simplest case. The space-time geometry outside a perfectly spherical, non-rotating mass. The result was the Schwarzschild metric, a mathematical description of how space-time is curved by such a mass. Schwarzschild sent his solution to Einstein, who was impressed and presented it to the Prussian Academy of Sciences on Schwarzschild's behalf. Sadly, Schwarzschild died a few months later from an illness contracted at the front. The Schwarzschild solution contained something strange and disturbing. At a certain radius from the center of any mass, now called the Schwarzschild radius, the mathematics seemed to break down. The equations produced infinities, what mathematicians call a singularity. For the Sun, the Schwarzschild radius would be about 3 kilometers, meaning you would have to compress the entire Sun into a sphere 3 kilometers in radius to reach this critical threshold. For the Earth, it is about 9 millimeters. These numbers are so far inside the actual extent of the Sun and Earth that they seemed physically irrelevant. No one thought you could actually compress the Sun into 3 kilometers. The singularity was widely dismissed as a mathematical curiosity, an artifact of the simplifying assumptions, not a real physical phenomenon. But over the following decades, physicists gradually came to realize that the Schwarzschild radius and the bizarre geometry it implied might be physically real after all. The key insight was about stellar evolution and what happens when a massive star runs out of fuel. Stars shine because they are powered by nuclear fusion in their cores. For a star like the Sun, hydrogen nuclei fuse together to form helium, releasing enormous amounts of energy in the process. This energy creates an outward pressure that supports the star against the crushing inward pull of its own gravity. The star is in equilibrium, gravity pulling in, radiation pressure pushing out, the two forces balanced. But this cannot last forever. Eventually the fuel runs out. For the Sun, the end will come in about 5 billion years. As the core hydrogen is exhausted, the core will contract while the outer layers expand, and the Sun will become a red giant swelling to engulf the inner planets. Eventually, the outer layers will be shed entirely, leaving behind the burned-out core, a white dwarf. A hot, dense ball of carbon and oxygen, roughly the mass of the Sun compressed into the size of the Earth. A white dwarf is supported against further collapse not by nuclear burning, but by a quantum mechanical phenomenon called electron degeneracy pressure. The Pauli exclusion principle of quantum mechanics forbids two electrons from occupying the same quantum state. and this creates an effective pressure that resists compression even in the absence of any heat source. White dwarfs will slowly cool and fade over billions of years, eventually becoming cold, dark objects called black dwarfs. Though the universe is not yet old enough for any black dwarfs to have formed. For more massive stars, the story is more dramatic. Stars several times more massive than the Sun can continue fusing heavier and heavier elements, helium, carbon, oxygen, silicon, until they reach iron. Iron is the end of the road for fusion. Fusing iron does not release energy. It requires energy. When the iron core of a massive star reaches a critical mass, the quantum mechanical pressure that was supporting it can no longer hold. The core collapses catastrophically in less than a second, reaching nuclear density, the density of an atomic nucleus, and then bouncing back in a stupendous explosion. A core collapse supernova. The outer layers of the star are blasted into space, and what remains is either a neutron star or, for the most massive progenitors, a black hole. A neutron star is an exotic and extreme object, a ball of nuclear matter roughly 20 kilometers in diameter, containing more mass than the Sun, spinning sometimes hundreds of times per second, with magnetic fields trillions of times stronger than Earth's. But even neutron stars have a limit. Just as electron degeneracy pressure has a maximum mass it can support, the Chandrasekhar limit for white dwarfs. About 1.4 solar masses. Neutron stars have an analogous limit somewhere between 2 and 3 solar masses, depending on the equation of state of ultra-dense nuclear matter, which we do not fully understand. If the remnant core exceeds this limit, nothing can stop the collapse. Gravity wins completely. The matter continues to compress past nuclear density, through any hypothetical quark star phase, all the way down to a mathematical point of infinite density, the singularity. And around this singularity, the geometry of space-time is so severely distorted that the Schwarzschild radius becomes a physical reality. The event horizon. The event horizon is the boundary of a black hole. It is not a physical surface. There is no wall there, no membrane, nothing you could touch. But it is a point of no return. Once anything, matter or light, crosses the event horizon, it can never escape. The curvature of space-time inside the event horizon is so extreme that all paths through space-time lead inevitably toward the central singularity. Space itself, inside the event horizon, flows inward faster than light can travel. This is the key point. It is not that objects inside the event horizon are moving too slowly to escape. It is that the geometry of space-time itself is dragging everything toward the center faster than light can move outward. And since nothing can travel faster than light, escape is impossible. From the outside, a black hole is characterized by just 3 quantities: its mass, its electric charge, and its angular momentum, spin. This remarkable simplicity is captured in the no-hair theorem, which states that all other information about what formed the black hole is lost. Whether the black hole formed from a collapsed star made mostly of hydrogen, or from a collapsed star made mostly of iron, or from 1 billion tons of rubber ducks, the black hole looks exactly the same, characterized only by its mass, charge, and spin. All other details, the hair of the original matter, are gone. For a long time, physicists assumed that black holes were stable, eternal objects. Once formed, they would persist indefinitely. There was no mechanism within general relativity for a black hole to lose mass and disappear. The event horizon, once established, could only grow larger as more matter fell in. In 1971, Hawking himself proved a powerful theorem. The total area of all event horizons in the universe can only ever increase, never decrease. This seemed to confirm the permanence of black holes. They could grow, but they could not shrink. And yet there was a curious parallel that several physicists noticed. The laws governing black holes seem to mirror almost perfectly the laws of thermodynamics. Thermodynamics is the science of heat, energy, and entropy. A set of fundamental laws governing how energy flows and how disorder evolves in physical systems. The 4 laws of thermodynamics are among the most fundamental and inviolable principles in all of science. And in the early 1970s, it became apparent that for every thermodynamic law, there was an analogous law for black holes. The 0th law of thermodynamics states that a system in thermal equilibrium has a uniform temperature throughout. The analogous law for black holes states that a stationary black hole has a uniform surface gravity across its entire event horizon. The 1st law of thermodynamics states that energy is conserved. The total energy of a system changes only by the addition or removal of heat or work. The analogous law for black holes relates changes in a black hole's mass to changes in its area, angular momentum, and charge. The 2nd law of thermodynamics is the famous entropy law. The total entropy of a closed system always increases or stays the same, never decreases. The analogous law for black holes is Hawking's area theorem. The total area of event horizons can never decrease. The 3rd law of thermodynamics states that absolute 0 temperature cannot be reached by any finite process. The analogous law for black holes states that a black hole with 0 surface gravity cannot be created in a finite number of steps. This parallel was striking, but for a while it was treated as just that. A formal mathematical analogy, perhaps suggestive but not necessarily deep. The problem was that thermodynamics requires objects to have temperature and entropy, and temperature means the emission of thermal radiation. A hot object glows. Its temperature is related to the spectrum of light it emits. But black holes, by definition, do not emit anything. How could they have a temperature? The idea seemed absurd. A young physicist named Jacob Bekenstein pushed the analogy harder than anyone. He argued that black holes must have a genuine physical entropy, not just a formal analogy to entropy. His reasoning was elegant and thermodynamic. Entropy, in the statistical mechanics of Boltzmann, is a measure of the number of microscopic states consistent with a given macroscopic state, roughly a measure of disorder or missing information. If you throw a cup of coffee into a black hole, you might worry that you have destroyed the entropy of the coffee, violating the second law of thermodynamics by decreasing the total entropy of the universe. But Bekenstein argued that the black hole's entropy must increase to compensate, and that the entropy of the black hole is proportional to the area of its event horizon. The more mass falls into the black hole, the larger the event horizon grows, and the larger the entropy. The second law is not violated. The entropy is not lost. It is absorbed into the black hole and reflected in the growth of its horizon. Bekenstein's argument was beautiful but controversial. Hawking was initially skeptical. If black holes have entropy, they must have temperature. And if they have temperature, they must emit radiation. And that, Hawking thought, was obviously impossible. You cannot get radiation out of a black hole. But then Hawking did the calculation, and what he found changed physics forever. The calculation required combining general relativity, the theory of curved space-time and gravity, with quantum field theory, the quantum mechanical description of particles and fields. This combination, called quantum field theory in curved space-time, is technically ferociously difficult. The mathematics is formidable, but Hawking pushed through it, and what he found was that the event horizon of a black hole does not simply sit quietly in the vacuum of space. Instead, the combination of the black hole's intense gravitational field and the quantum mechanical nature of the vacuum causes the black hole to emit a steady stream of thermal radiation, as if it were a warm body. This radiation is now called Hawking radiation. To understand where Hawking radiation comes from, we need to understand what quantum mechanics says about empty space. In classical physics, empty space is exactly that, empty. A perfect vacuum contains nothing, no matter, no energy, no fields. But in quantum mechanics, this picture is radically wrong. The vacuum is not empty. It is a seething, roiling sea of quantum fluctuations. This is a consequence of the Heisenberg uncertainty principle, one of the foundational principles of quantum mechanics. The uncertainty principle states that certain pairs of physical quantities cannot both be precisely determined at the same time. The more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. A related form of the uncertainty principle applies to energy and time. The uncertainty in the energy of a system multiplied by the uncertainty in the time over which the energy is measured must be at least as large as Planck's constant divided by 4p. This means that over very short time intervals, the energy of a system is inherently uncertain. It can fluctuate significantly. The consequence is that even in a perfect vacuum, the electromagnetic field, and indeed all quantum fields, cannot simply be zero everywhere. Quantum uncertainty forbids a field from having a precisely defined value of zero with a precisely defined rate of change of zero. Fields are constantly fluctuating, and these fluctuations have real physical consequences. One of the most dramatic is the creation of virtual particle-antiparticle pairs. The idea of virtual particles is often misunderstood and sometimes criticized as merely a mathematical bookkeeping device. But their physical effects are real and measurable. According to quantum field theory, the vacuum is constantly producing pairs of particles and antiparticles, an electron and a positron, say, or a quark and an antiquark, that pop into existence together, exist for a fantastically short time, and then annihilate each other, disappearing back into the vacuum. Energy is conserved overall because the pair borrows energy from the vacuum for a brief moment and then returns it when the pair annihilates. The time for which the pair can exist is limited by the uncertainty principle. The more energetic the pair, the shorter its allowed lifetime. Under ordinary circumstances in flat, empty space far from any masses, these virtual pairs are created and annihilated in the tiniest fractions of seconds with no lasting effect. They are real in the sense that they affect the properties of quantum systems measurably. The Casimir effect, the Lamb shift in hydrogen spectrum, but they do not produce any net radiation or energy flow. Near the event horizon of a black hole, however, something remarkable happens. The virtual pairs are still being created everywhere, including just outside the event horizon. But here, the intense gravitational field of the black hole can intervene before the pair has a chance to annihilate. If one member of the pair falls into the black hole while the other escapes to infinity, they can never come back together to annihilate. The escaping particle becomes real. It has enough energy to exist as a genuine propagating particle, and it flies away from the black hole as radiation. The other particle falls into the black hole. But wait, if the black hole is absorbing a particle, shouldn't it gain mass? That is the naive expectation. But the mathematics tells a more subtle story. In quantum field theory, virtual particles do not have well-defined positive energies in all reference frames. Near the event horizon, one of the virtual pair can have negative energy as measured from far away. A concept that makes sense in the curved space-time geometry near the horizon, even though it would be forbidden in flat space. When this negative energy particle falls into the black hole's total energy, and hence its mass, decreases. Meanwhile, the positive energy partner escapes to infinity as real radiation. The net result is that the black hole radiates energy and loses mass. Hawking computed the spectrum of this radiation and found something remarkable. It is a perfect thermal spectrum, the same kind of radiation emitted by any warm body in thermal equilibrium. This is called black body radiation. The temperature of the radiation is inversely proportional to the mass of the black hole. The formula, now known as the Hawking temperature, is elegantly simple. The temperature equals the Planck constant times the speed of light cubed divided by the product of 8 times pi. Newton's gravitational constant, the Boltzmann constant, and the black hole's mass. Or in shorthand, T is proportional to 1m. This inverse relationship between temperature and mass is crucial. A more massive black hole is colder, and a less massive black hole is hotter. A stellar mass black hole, say 10 times the mass of the Sun, has a Hawking temperature of about 6 billionths of a Kelvin. The current temperature of the cosmic microwave background radiation, the thermal afterglow of the Big Bang, is about 2.7 Kelvin. So a stellar mass black hole is actually absorbing far more energy from the cosmic microwave background than it is emitting as Hawking radiation. It is effectively gaining mass, not losing it, in the current epoch of the universe. The Hawking radiation is completely swamped by the ambient radiation of the universe. But the universe is expanding and cooling. The cosmic microwave background temperature decreases as the universe expands. Eventually, billions upon billions of years from now, the cosmic microwave background will have cooled to below the Hawking temperature of even stellar mass black holes, and they will begin to lose mass on net. And for smaller black holes, or once the CMB temperature drops sufficiently, Hawking radiation dominates and the black hole genuinely shrinks. As the black hole loses mass by emitting Hawking radiation, its temperature increases because temperature is inversely proportional to mass. As temperature increases, the rate of radiation increases. A hotter black body radiates more power. So as the black hole shrinks, it radiates more and more intensely, which causes it to shrink faster, which causes it to radiate even more intensely. This is a runaway process, a feedback loop that accelerates without limit as the black hole's mass approaches zero. In the final stages of a black hole's life, it radiates explosively, releasing its remaining mass energy in an intense burst of high-energy gamma rays and other particles. And then it is gone. The time it takes for a black hole to evaporate completely depends on its initial mass. Hawking worked out the formula. The evaporation time is proportional to the cube of the initial mass. More precisely, it is proportional to m cubed with a coefficient involving the fundamental constants of nature. For a black hole of 1 solar mass, the evaporation time works out to be on the order of 10 to the power of 67 years. The current age of the universe is about 13.8 billion years, or roughly 10 to the power of 10 years. So a solar mass black hole would take about 10 to the 57 times the current age of the universe to evaporate. That is an incomprehensibly long time for the supermassive black holes at the centers of galaxies. The largest known has about 40 billion solar masses. The evaporation time is unimaginably longer. The evaporation time scales as the cube of the mass. So a black hole 40 billion times more massive than the Sun would evaporate in a time roughly 10 to the 30th power times longer than a solar mass black hole. These timescales are so vast they dwarf any natural timescale we can conceive. The protons in ordinary matter are expected to decay, and if proton decay occurs at all, on timescales of around 10 to the 34 years or longer, the last stars in the universe will flicker out within a few tens of trillions of years. The universe will be a dark, cold, sparse place of black holes and dead stellar remnants long before the largest black holes even begin to noticeably evaporate. But evaporate they will. The mathematics is inexorable. The universe is not infinitely old, and entropy always increases. No matter how long it takes, every black hole that has ever formed will eventually radiate away the last of its mass in a final flash, and silence will fall. Now, Hawking's result raises one of the deepest and most troubling questions in all of physics. A question that has occupied theorists for 5 decades and remains even now incompletely resolved. It is called the black hole information paradox, and it strikes at the heart of what it means for physical processes to be reversible. The laws of quantum mechanics at their deepest level are reversible. If you know the precise quantum state of a system at one time, you can in principle evolve it forward in time to find the state at any later time, and you can equally well evolve it backward in time to find the state at any earlier time. The quantum state contains all the information about the system, and the evolution of quantum states is unitary. A technical term meaning that information is conserved. No information is ever lost. This reversibility is one of the foundational features of quantum mechanics, deeply embedded in its mathematical structure. But Hawking radiation appears to violate this. Here is the problem. A star collapses to form a black hole. The star was composed of specific atoms in specific quantum states, encoding a specific amount of information. The black hole forms, and then it evaporates, emitting Hawking radiation. But Hawking's calculation shows that this radiation is purely thermal. It is random, like the radiation from a fire. The thermal radiation carries no information about what formed the black hole, no matter what fell in. Whether it was a star made of hydrogen or a star made of iron, a library of books or a collection of rubber ducks, the outgoing Hawking radiation looks exactly the same, perfectly thermal with no imprint of the infalling material. At the end, when the black hole has completely evaporated, all that remains is this featureless thermal radiation and the original quantum state of the star. All the specific information about exactly what the star was made of, in exactly what quantum states, appears to be gone forever. The final state of the universe after the black hole evaporates is a mixed quantum state. A state of maximum ignorance, not a pure quantum state that could be evolved backward to recover the initial conditions. This is a violation of unitarity. It is, if true, a genuine destruction of information. Something that quantum mechanics says cannot happen. This is the black hole information paradox. On one side, general relativity and the thermodynamics of black holes tell us that information falls into the black hole and is lost when the black hole evaporates. On the other side, quantum mechanics tells us that information can never be lost. Something has to give. But for decades, physicists could not agree on what. Hawking himself, for most of his life, accepted the radical conclusion: information is genuinely lost in black hole evaporation. Quantum mechanics, he thought, would have to be modified to allow for information loss in gravitational settings. But most of the physics community found this deeply unsatisfying. The unitarity of quantum mechanics is not just one feature among many. It is a load-bearing pillar of the entire theoretical framework. Abandoning it would require rebuilding physics nearly from scratch. The alternative, that information somehow escapes the black hole encoded in the Hawking radiation, requires that the radiation is not truly random, but actually carries subtle correlations that encode the original quantum state of whatever formed the black hole. In principle, if you collected all the Hawking radiation from the complete evaporation of a black hole and performed quantum measurements of extraordinary precision, you could reconstruct the original quantum state. You could recover the lost information, but this requires the information to somehow get out through the event horizon, which classically is impossible. This tension between the classical impossibility of information escape and the quantum mechanical requirement of information conservation drove some of the deepest work in theoretical physics over the last 50 years. A partial resolution came from an unexpected direction: string theory and the holographic principle. The holographic principle, developed by Gerard T. Hooft and Leonard Susskind in the 1990s, is one of the most startling ideas in modern physics. It proposes that all the information needed to describe the physics happening in a volume of space is actually encoded on the boundary of that volume, on a lower dimensional surface surrounding it. The analogy is to a hologram, which encodes a three-dimensional image on a two-dimensional surface. The holographic principle suggests that the universe itself is in some sense like a hologram. The three-dimensional world we experience might be the projection of information encoded on a two-dimensional boundary. The holographic principle received its most concrete realization in the anti-de Sitter conformal field theory correspondence, usually abbreviated ADS and CFT, developed by Juan Maldacena in 1997. ADS-CFT is a precise mathematical duality between two completely different theories, a theory of quantum gravity in a negatively curved, anti-de Sitter spacetime, and a quantum field theory without gravity defined on the boundary of that spacetime. The two theories are exactly equivalent. Any calculation in one can be done in the other, and the results agree. This duality is not speculative or approximate. It has been checked in countless specific calculations. And crucially, the boundary theory, the quantum field theory without gravity, is manifestly unitary. Information is conserved. The evolution is reversible. If ADS-CFT is correct, then the gravitational theory inside the anti-de Sitter space must also be unitary, because it is equivalent to the unitary boundary theory, and this means that black hole evaporation in ADS spacetime must be a unitary process. Information cannot be lost. The Hawking radiation must somehow encode the original information, however subtly. The information paradox in this setting is resolved. Information is preserved, and the Hawking radiation is not truly thermal but carries subtle quantum correlations that encode the original state. But this resolution, while widely accepted among string theorists, raised a new paradox. If information escapes in the Hawking radiation, how does it get out? The classical picture says that the event horizon is a point of no return. Once you are inside, you cannot send information out. For information to escape in the Hawking radiation, the radiation emitted outside the horizon would have to be quantum correlated with the radiation emitted later, in a very specific way. In 2012, Almheri, Marov, Polchinski, and Sully, the group known as AMPS, pointed out a devastating inconsistency in trying to maintain both unitarity and the equivalence principle. The equivalence principle is one of the foundational principles of general relativity. It states that a freely falling observer experiences no gravity locally. The effects of gravity are indistinguishable from those of an accelerating reference frame, and in a freely falling frame, the laws of physics are the same as in flat spacetime. For an observer falling into a large black hole, this means that they should not notice anything special as they cross the event horizon. The event horizon is not a physical surface, it is a mathematical boundary. A falling observer has no local way to detect when they have crossed it. AMPS showed that this cannot be reconciled with unitarity in a straightforward way. If information escapes in the Hawking radiation, specifically if the late Hawking radiation is maximally entangled with the early Hawking radiation, as unitarity requires, then the infalling observer cannot have the smooth, uneventful horizon crossing that the equivalence principle demands. Instead, the AMPS argument suggests the infalling observer would hit a wall of high-energy radiation at the horizon, a firewall that would instantly destroy them. The firewall is the quantum price of unitarity. The firewall paradox, also called the AMPS paradox, presented a trilemma. You cannot simultaneously maintain unitarity, information conservation, the equivalence principle, smooth horizon crossing, and the semi-classical validity of Hawking's calculation. At least one of these must be wrong. Each option leads to profound revisions of our understanding. If unitarity fails, quantum mechanics must be modified. If the equivalence principle fails at the horizon, general relativity must be modified. If Hawking's semi-classical calculation is wrong in a more subtle way, then our understanding of quantum field theory in curved spacetime is inadequate. Resolving the firewall paradox has been one of the central problems in theoretical physics since 2012. Several proposals have been put forward. One influential idea developed by Maldacena and Susskind is called ER turns EPR. The name combines two famous thought experiments. ER stands for Einstein-Rosen bridges, the technical name for what are popularly called wormholes. Shortcuts through space-time that connect two distant regions. EPR stands for Einstein-Podolsky-Rosen, the thought experiment that introduced the idea of quantum entanglement, the quantum correlation between particles that Einstein famously called spooky action at a distance. The Sachs EPR conjecture proposes that these two phenomena are fundamentally the same thing. Quantum entanglement between particles is equivalent to a microscopic wormhole connecting them. If two particles are maximally entangled, they are connected by a wormhole. This would provide a mechanism for information to escape. It flows out through Planck-scale wormholes connecting the interior of the black hole to the outgoing Hawking radiation. More recently, significant progress on the information paradox has come from a different approach involving so-called islands in the space-time geometry. In 2019, calculations by Pennington and independently by Almheri, Mahajan, Maldacena, and Zhao showed that including quantum gravitational contributions, specifically saddle points in the path integral over geometries called replica wormholes, to the calculation of the entropy of Hawking radiation changes the result dramatically at late times. The entropy of the Hawking radiation calculated semi-classically the way Hawking did increases monotonically forever, but the corrected calculation, including replica wormholes, shows that the entropy first increases and then, at the page time, when the black hole has radiated away roughly half its initial entropy, begins to decrease. This decreasing entropy is exactly what unitarity requires. It means the Hawking radiation is gradually encoding more and more information, and by the time the black hole has fully evaporated, all the information has been returned to the outside world. The Page curve, named after physicist Don Page, who first argued in the 1990s that this is what unitarity requires, is recovered. These are extraordinarily sophisticated developments, and they are not fully understood. The replica wormhole calculation is technically formidable, and it is not entirely clear what the physical mechanism is by which information escapes. The island formula, which computes the entropy of the Hawking radiation by including contributions from island regions inside the black hole, gives the right answer in terms of recovering unitarity. But the precise physical picture of how this works remains debated. We are in the middle of a revolution in our understanding of black holes, quantum mechanics, and the nature of space-time, and the final picture has not yet emerged. But amid all this uncertainty, one thing remains clear and well established. Hawking radiation is real. Black holes do evaporate, and no black hole lasts forever. The debate is not about whether black holes evaporate, but about the details of what happens to the information encoded in the infalling matter. The fundamental reality of Hawking evaporation, the slow but inexorable loss of mass from every black hole, is on solid theoretical footing. Let us return from these theoretical heights to think about the practical reality of black hole evaporation and what it means for the long-term fate of the universe. In the very far future, trillions upon trillions of years from now, the universe will be a profoundly different place from the one we inhabit. The current age of the universe, 13.8 billion years, will seem like an unimaginably brief initial moment. Stars like the Sun live for about 10 billion years. The smallest, coolest, most miserly red dwarf stars can live for trillions of years, 100 times longer than the current age of the universe. But even they will eventually exhaust their hydrogen and die. Within about 100 trillion years, 10 to the 14 years, the last stars will have burned out. The universe will enter what cosmologists call the degenerate era, a dark period populated by dead stellar remnants, white dwarfs, neutron stars, black dwarfs, and black holes. In the degenerate era, structure will slowly decay. White dwarfs will gradually cool, radiating their residual heat into the cosmic void over time scales of quadrillions of years. Neutron stars will similarly cool and fade. Galaxies will slowly lose stars through gravitational interactions. Some stars being flung into intergalactic space, while the galactic core, typically a supermassive black hole, grows by absorbing other stars. Over time scales of 10 to the 20 years, galaxies will dissolve into darkness, leaving only their central black holes. If protons are stable, which we do not yet know for certain, dead stars will persist as cold, dark objects for essentially forever. But if proton decay occurs, as predicted by many grand unified theories of particle physics, then on timescales of around 10 to the 40 years, all the baryonic matter in white dwarfs and neutron stars will have decayed into radiation and leptons. Only black holes will remain, and then one by one the black holes will evaporate. The smallest black holes, hypothetical primordial black holes formed in the early universe with masses much smaller than the Sun, will evaporate first. Black holes of stellar mass will evaporate over timescales of around 10 to the 67 years. The supermassive black holes at the centers of the largest galaxies with masses of billions of solar masses will take around 10 to the 100 years or more, a Google years, to evaporate. As each black hole evaporates, it will release its mass as a final burst of Hawking radiation. A brief flash of gamma rays, neutrinos, electrons, positrons, and other particles, concentrated in the final fraction of a second of the black hole's life. After the last black hole evaporates, after the black hole era ends, perhaps around 10 to the 100 years from now, the universe will be an unimaginably cold, dark, diffuse sea of photons and neutrinos, slowly cooling and spreading forever. This is the ultimate fate predicted by thermodynamics. Maximum entropy, heat, death. No more complex structures, no gradients of temperature, no usable energy. Just a thin, cold gas of radiation spreading forever through an expanding void. It is a somber vision, but it is also, in a strange way, beautiful. The universe obeys laws. Entropy increases. Nothing lasts forever. Not stars, not galaxies, not black holes. The second law of thermodynamics is the most universal law in physics, and it tells us that the universe is on an one-way journey from order to disorder, from low entropy to high entropy, and that nothing, not even the most massive and powerful objects in the cosmos, can escape this journey. There is a profound philosophical dimension to all of this. The impermanence of black holes discovered by Hawking in 1974 was in some sense the extension of thermodynamic inevitability to the farthest reaches of space-time and the most extreme objects in the universe. Before Hawking, one might have imagined that black holes were the universe's way of hiding things permanently, of creating genuine exceptions to the march of entropy and time. A black hole seemed to be a perfect trap, immune to the decay that afflicts all other things. Hawking showed this is not so. Even black holes obey thermodynamics. Even black holes have temperature and entropy. Even black holes age and die. The discovery of Hawking radiation also did something else. It revealed for the first time a genuine physical regime where all three of the great pillars of modern physics, general relativity, quantum mechanics, and thermodynamics, must be combined simultaneously to understand what is happening. Each of these theories on its own is extraordinarily powerful and precise. but they were developed in different contexts with different mathematical languages, and combining them is technically and conceptually difficult. General relativity operates on the scale of planets, stars, galaxies, and the universe itself. It describes the large-scale geometry of space-time. Quantum mechanics operates on the scale of atoms, molecules, and subatomic particles. It describes the probabilistic, discrete, wave-like behavior of matter and energy at the smallest scales. Thermodynamics is a more general framework that transcends scales, describing the statistical properties of systems with many degrees of freedom, the flow of heat and the increase of entropy. Each of these theories works magnificently in its own domain. But at the event horizon of a black hole, all three are needed at once. The curvature of space-time is extreme, requiring general relativity. The vacuum fluctuations that give rise to Hawking radiation are quantum mechanical, and the thermal spectrum of the radiation and the entropy of the black hole require thermodynamics. Hawking radiation is the only known physical phenomenon that requires all three simultaneously. This is part of why it is so important theoretically, and why its implications have been so far-reaching. The quest to properly combine quantum mechanics and general relativity into a single consistent theory, quantum gravity, is the great unsolved problem of theoretical physics. The two theories are mathematically incompatible in their current forms. General relativity is a classical theory. It describes smooth, continuous fields in space-time without quantum uncertainty. Quantum mechanics and quantum field theory is inherently probabilistic and discrete. When you try to combine them naively, applying the methods of quantum field theory to general relativity, you get infinities that cannot be renormalized. The theory makes predictions of infinite probability for many physical processes, which means it is failing outside its domain of validity. String theory is the most developed attempt to solve this problem. It proposes that the fundamental entities in nature are not point-like particles, but tiny, vibrating one-dimensional strings. Different vibrational modes of these strings correspond to different particles. String theory naturally incorporates gravity. The graviton, the hypothetical quantum of the gravitational field, emerges automatically as one of the vibrational modes of the string, and it avoids the infinities that plague naive quantum gravity by spreading interactions out over the finite extent of the string, rather than localizing them at a point. It also makes the prediction that there must be additional spatial dimensions beyond the three we observe, curled up at scales too small to detect directly, and it led naturally to the ADS-CFT correspondence, which has been so important for understanding the black hole information paradox. Loop quantum gravity is an alternative approach that is less well developed but has its advocates. It proposes that space-time itself is quantized at the Planck scale. the smallest meaningful length about 10 to the 35 meters, and has a discrete structure like a foam at those scales, rather than adding new dimensions or fundamental entities like strings. Loop quantum gravity tries to directly quantize the geometry of space-time using sophisticated mathematical techniques derived from the canonical quantization of general relativity. Both string theory and loop quantum gravity, in different ways, suggest that the smooth, continuous space-time of general relativity is an approximation that breaks down at the Planck scale, just as classical smooth fluids are an approximation to the discrete molecular reality. And both suggest that the singularity at the center of a black hole, the point of infinite density and infinite curvature where general relativity breaks down completely, is replaced by something finite and well-defined in the full quantum theory. The singularity is likely not real, but is instead a signal that general relativity is being pushed beyond its domain of validity. This is important for the story of black hole evaporation. Hawking's calculation assumes that the event horizon is a region of smooth, weakly curved space-time, where quantum field theory in curved space-time is a valid approximation. Far from the singularity near the event horizon of a large black hole, this is a reasonable assumption. The curvature at the event horizon of a solar mass black hole is large but manageable. For a supermassive black hole millions of times more massive than the Sun, the curvature at the event horizon is actually quite mild. Mild enough that a person falling through it would not even notice at first. In these regions, Hawking's calculation should be trustworthy. But in the final moments of evaporation, when the black hole has shrunk to near the Planck mass, about 22 micrograms, an absurdly small mass for something that started as a stellar remnant, but the smallest mass at which the concept of a semi-classical black hole is meaningful. The curvature at the horizon becomes Planckian, and quantum gravitational effects dominate. At this point, Hawking's calculation breaks down. We do not have a reliable theory of what happens in the final Planck time moments of a black hole's evaporation. There may be a Planck mass remnant left over. There may be an explosion of high-energy Planck particles. There may be some exotic, non-perturbative process we have not yet conceived. The final fate of the evaporation singularity is unknown, and cannot be known without a complete theory of quantum gravity. But this uncertainty about the final instant does not undermine the main conclusion. Black holes evaporate. The vast majority of the evaporation, from stellar mass down to near the Planck mass, is governed by Hawking's calculation, which is solid. The black hole loses essentially all of its mass during this well-understood phase. What happens in the last tiny fraction of a second is genuinely uncertain. But whatever happens, the black hole as we know it is gone. A black hole cannot last forever. The discovery of Hawking radiation also has profound implications for our understanding of entropy and the arrow of time. The second law of thermodynamics tells us that entropy always increases. This is ultimately a statistical law. It is overwhelmingly probable that entropy increases because there are enormously more disordered states than ordered ones, and systems tend to evolve toward higher entropy configurations. But it is not a fundamental law in the sense of being derivable from first principles. It is emergent from the statistics of many body systems. The arrow of time, the fact that time seems to flow in one direction from past to future and not the other, is intimately connected to the second law. At the level of fundamental physics, most laws are time-symmetric. They work the same whether you run time forward or backward. But the second law breaks this symmetry at the macroscopic level. Entropy was low in the past and will be high in the future. This is what gives time its direction. Black holes are deeply connected to the arrow of time through their entropy. Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, with the proportionality constant being the Boltzmann constant divided by 4 times the Planck area. This is the Bekenstein-Hawking entropy formula, and it is one of the deepest results in theoretical physics. For a solar mass black hole, this entropy is staggeringly large, about 10 to the 77 in natural units, enormously larger than the entropy of the star that collapsed to form it. In fact, a black hole of a given mass has the maximum entropy of any object of that mass and size. It is the most disordered possible configuration of matter. This makes sense from an information-theoretic perspective. Once matter has fallen into a black hole and all you can observe from outside is the mass, charge, and spin, all other information is lost, or at least inaccessible, from the outside. The black hole represents a kind of ultimate erasure of structure, a triumph of disorder over order. Except that Hawking showed this is not truly final. The black hole radiates, loses mass, shrinks, and eventually evaporates. And if unitarity is preserved, if information is not truly lost but encoded in the correlations of the Hawking radiation, then the process is in principle reversible. The information is not destroyed, it is scrambled, hidden in the statistical correlations of the outgoing radiation but theoretically recoverable. The black hole is an extraordinarily efficient information scrambler, perhaps the most efficient possible, but not an information destroyer. This perspective connects to the concept of computational complexity. It has been suggested by Susskind and others that the interior volume of a black hole, which keeps growing even after the black hole has stopped gaining mass from outside, thanks to the geometry of space-time, is related to the computational complexity of the quantum state of the black hole. As the black hole ages and evaporates, the computational complexity of reconstructing the original quantum state from the Hawking radiation grows. By the time the black hole is fully evaporated, recovering the information from the radiation would require performing a computation of extraordinary complexity, involving exponentially many quantum operations on all the emitted radiation. This is information recovery in principle, but not in practice. No civilization, however advanced, could realistically perform such a computation on the output of a black hole evaporation. In this sense, black holes are like cosmic scramblers. They take quantum information in, process it in ways governed by the physics of the horizon and the Hawking process, and release it in a form that is theoretically recoverable but practically inaccessible. The information is there, but it is hidden in the correlations of the radiation in a way that requires perfect knowledge of every emitted quantum to decode. In practice, the information is as lost as it can be, but in principle, in the austere perfection of the mathematical laws, it survives. Let us take stock. We have seen that black holes form from the collapse of massive stars and from the mergers of compact objects. We have seen that they are characterized by event horizons beyond which nothing can escape, not even light. We have seen that classical general relativity seems to make them eternal and stable, but we have also seen that quantum mechanics, applied to the curved space-time near the event horizon, predicts the emission of Hawking radiation, a slow, steady thermal glow that carries energy away from the black hole, causing it to lose mass over time. This process is incredibly slow for the massive black holes that populate the current universe, but it is inexorable, given sufficient time. Times ranging from 10 to the 67 years for stellar mass black holes to 10 to the 100 years for the most massive known black holes. Every black hole will evaporate completely. The discovery of this process was one of the great triumphs of 20th century theoretical physics. It was not predicted by experiment or guided by observation. There is no way with current technology to detect Hawking radiation from astrophysical black holes, since it is far too faint. It emerged purely from theoretical reasoning, from Hawking's audacious combination of general relativity, quantum field theory, and thermodynamics. And it revealed that the universe is more unified, more governed by common laws than even the experts had suspected. Even the most extreme objects obey thermodynamics. Even the most fearsome gravitational prisons slowly bleed away into radiation. In a universe governed by the second law of thermodynamics, there is no such thing as a permanent prison, even for light. Given enough time, everything changes. Stars burn out, galaxies dissolve, protons decay, and black holes evaporate. The universe moves relentlessly and irreversibly toward greater and greater entropy, toward heat death, toward a final state of cold, diffuse equilibrium in which no further change is possible. because there are no more gradients of energy to exploit, no more low-entropy reservoirs to draw upon. In this context, the impossibility of permanent black holes is not a surprising fact, but an almost inevitable consequence of the deepest laws of physics. Entropy always increases. Systems always evolve toward their highest entropy states. Black holes, despite their extreme and exotic nature, are not exempt. They have entropy, they have temperature, they emit radiation, and over cosmic timescales they evaporate. The universe does not make exceptions, not even for the most extreme concentrations of mass and gravity in existence. And yet, in another sense, the discovery is genuinely surprising, because it required a synthesis of ideas that no one expected to belong together. Who would have guessed before Hawking that quantum mechanics had anything to say about the event horizons of black holes? Who would have imagined that the vacuum of space, properly understood through quantum field theory, would glow near a gravitational abyss? Who would have predicted that the entropy of a black hole would be written in the geometry of its event horizon, rather than in the arrangement of the matter inside? These connections were not obvious. They emerged from deep theoretical work, from the willingness to take the mathematical implications of our best theories seriously, to follow the equations wherever they led, even when the destination was unexpected. This is what makes Hawking radiation such an important result, even beyond its specific content. It is a demonstration of the power of theoretical physics to reveal deep truths about nature that experiment has not yet, and in some cases may never, directly probe. It is a reminder that our most fundamental theories, when taken seriously and combined carefully, contain far more information about the universe than we might initially suppose. And it is a humbling illustration of the fact that the universe, for all its majesty and scale, operates according to principles that can be understood, that are accessible to human reason, that have been and continue to be uncovered by the patient, creative, rigorous work of science. The impossibility of eternal black holes is, in the end, a profound statement about the nature of time and the structure of physical law. In a universe with thermodynamics, with quantum mechanics, with general relativity, nothing can be forever. Not mountains, not stars, not black holes. Not even, some have speculated, the protons themselves. Everything that exists now was created at some point in the past. And everything that exists now will, on some time scale, cease to exist in its current form. This impermanence is not a flaw in the universe's design, but a fundamental feature of its physics. Hawking understood this deeply, and his discovery of black hole evaporation was one of the greatest intellectual gifts he gave to science. It is perhaps fitting that a man who spent much of his life in the confines of a wheelchair, trapped by the progressive paralysis of motor neuron disease, should have discovered that even the most extreme physical prisons in the universe, regions of space-time from which not even light can escape, are ultimately temporary. Given enough time, even a black hole finds its way out, not through any conventional channel, not by violating the laws that constrain it, but through the subtle, patient work of quantum mechanics on the fabric of space-time itself. We do not yet have a complete theory of quantum gravity. We do not fully understand what happens in the final moments of a black hole's evaporation. We have not directly detected Hawking radiation from any astrophysical object. But we have, thanks to Hawking and the generations of physicists who built on his work, a profound and mathematically rigorous understanding of why black holes cannot last forever. They radiate, they shrink, they die, and in their death, they return their mass energy to the universe, contributing, after an almost incomprehensibly long delay, to the final dispersal of all the energy and information in the cosmos. The universe is patient, but it is also just. Nothing that begins can avoid its ending, not even a black hole. Of all the forces in nature, gravity is at once the most familiar and the least understood. We feel it every moment of our lives. It governs the orbits of planets and the structure of the cosmos, and yet at the quantum level it remains mysterious, resistant to the unification that has been achieved for the other fundamental forces. The electromagnetic force, the weak nuclear force, and the strong nuclear force have all been successfully described by quantum field theories. The standard model of particle physics, which is one of the most precisely tested theories in the history of science. Gravity alone stands apart. Einstein's general relativity is magnificent and correct at the scales for which it was designed, but it is a classical theory, and when pushed to the quantum level it becomes inconsistent. Black holes are the arena where this inconsistency is most sharply exposed. They are regions where gravity is so strong that the curvature of space-time becomes extreme, and near the singularity it becomes truly infinite. At the singularity, general relativity fails completely. It predicts infinite densities and curvatures, which is its way of signaling that the theory is being used outside its domain of validity. The singularity is not a physical object. It is a breakdown of the mathematics of general relativity. A true theory of quantum gravity would, we believe, smooth out the singularity and provide a sensible description of what happens at the center of a black hole. Similarly, the event horizon is a region where quantum effects cannot be ignored, as Hawking showed. The event horizon is a macroscopic structure. For a stellar mass black hole, it has a radius of a few kilometers, but it is nevertheless the site of quantum mechanical processes that have macroscopic consequences. Hawking radiation is one such consequence. The firewall paradox and the information paradox are symptoms of the deeper inconsistency between quantum mechanics and general relativity, playing out at the event horizon. Resolving these paradoxes is not merely an academic exercise. Understanding what happens to information at a black hole's event horizon and in its interior is intimately connected to understanding the nature of space-time itself, the origin of the universe, and the ultimate fate of physical law. The reason these questions matter so much is that they are pointing us toward a deeper theory of nature, one that unifies the quantum and the gravitational, one that tells us what space-time really is at the most fundamental level. Some of the most fascinating recent work suggests that space-time itself, the smooth four-dimensional manifold that general relativity describes, is not fundamental but emergent. In the ADS CFT picture, the bulk space-time arises from the quantum entanglement structure of the boundary field theory, the connectivity of space-time. The fact that different regions are close to each other corresponds to the entanglement between different degrees of freedom in the boundary theory. When entanglement is strong, regions of space-time are close together. When entanglement is weak or absent, regions are far apart or disconnected. This idea that entanglement is literally the glue that holds space-time together is called the Space-Time from Entanglement Program, and it is one of the most active areas of research in quantum gravity. In this picture, a black hole is a region where the entanglement structure of the boundary theory is highly complex and scrambled. The information paradox arises because we are asking what happens to a region of space-time, the black hole interior, when the corresponding degrees of freedom on the boundary become maximally scrambled. The answer, according to recent calculations, is that the interior space-time geometry is reconstructed not from local degrees of freedom on the boundary but from non-local entanglement across the boundary. The island that appears in the calculation of the page curve is a region of the interior space-time that is effectively reconstructed by outside observers through quantum entanglement, a tantalizing hint of the deep connection between entanglement and space-time geometry. These ideas are speculative but mathematically precise. They are not vague philosophical musings. They are based on concrete calculations in specific, well-defined theories, primarily the ADS and CFT correspondence. And they suggest a picture in which the dissolution of a black hole through Hawking evaporation corresponds, on the boundary, to the gradual disentanglement and simplification of the highly scrambled quantum state that represents the black hole. As the black hole evaporates, the complex entanglement structure that gave rise to the black hole's interior space-time gradually unravels, and the information that was scrambled in that structure is progressively encoded in the outgoing Hawking radiation. By the time the black hole is gone, all the information has been returned to the outside world, hidden in the quantum correlations of the radiation. This is not a story about black holes as cosmic criminals who destroy information, evading justice until caught by Hawking's quantum mechanical sheriff. It is a story about the universe's deep commitment to consistency, to the conservation of information at the most fundamental level, and to the interconnectedness of space-time, entanglement, and thermodynamics. Black holes are extreme, but they are not exceptions. They obey the rules, and the rules say they cannot last forever. It is worth pausing to appreciate the scale of what has been understood. Human beings, living on a rocky planet orbiting an ordinary star in the outer suburbs of a middling galaxy, have used mathematical reasoning and careful observation to understand the behavior of objects containing billions of solar masses, located billions of light-years away, governed by physical laws that operate at scales ranging from the Planck length to the Hubble radius. We have determined not just what black holes are and how they form, but how they die, on timescales that are millions upon billions of times longer than the current age of the universe. This is one of the great achievements of the human intellect, and it rests on the accumulated work of generations of scientists from Newton to Einstein, from Boltzmann to Bekenstein, from Hawking to Maldacena and beyond. The story of black hole evaporation is also a story about the power of thought experiments and theoretical reasoning. We cannot wait around for a black hole to evaporate. Even the smallest astrophysical black holes will outlast any conceivable civilization by an enormous margin. We cannot detect the Hawking radiation from any known black hole with current or foreseeable technology. And yet we know with high confidence that black holes evaporate. We know this because our theoretical framework, the combination of general relativity, quantum mechanics, and thermodynamics, is internally consistent and has been validated in countless other contexts, and when applied to black holes it inescapably yields this result. The confidence is not absolute. No scientific conclusion is, but it is very high. If Hawking radiation is ever directly detected, it will most likely be through the evaporation of hypothetical primordial black holes. Tiny black holes formed in the early universe when quantum fluctuations in the density of matter were large enough to cause localized regions to collapse. If primordial black holes of sufficiently small mass were formed in the early universe, they would have evaporated by now, and some might be evaporating right now. The final burst of Hawking radiation from an evaporating primordial black hole would be a brief, intense burst of gamma rays, potentially detectable by gamma-ray observatories in space. No such signal has been convincingly detected, which constrains the abundance of primordial black holes of various masses. But the search continues, and detecting the final explosion of an evaporating primordial black hole would be one of the most spectacular observations in the history of astronomy. Direct experimental confirmation of Hawking's 40-year-old prediction. Until that day, If it comes, well, we are left with the mathematics, and the mathematics is unambiguous. Black holes emit Hawking radiation. This radiation carries energy away from the black hole. The black hole's mass decreases. As it shrinks, it gets hotter, radiates more intensely, and shrinks faster. Eventually, on timescales so vast they beggar the imagination, it vanishes in a final burst of energy, taking with it all the compressed complexity of whatever matter originally formed it, returning that energy in a dispersed high-entropy form to the universe at large. The universe is, in the end, governed by time and entropy. Everything that exists does so for a finite duration. Stars have lifetimes. Galaxies have lifetimes. Protons perhaps have lifetimes. And black holes, despite everything, have lifetimes. They are born in violence, in the gravitational collapse of massive stars or the mergers of compact objects. They live long lives, absorbing in falling matter, growing massive and quiet and cold. And they die slowly, by degrees, radiating away their mass in the patient, relentless trickle of Hawking radiation, until the last quantum of energy is gone and they wink out of existence, contributing their tiny share to the vast, cold, dark entropy of the dying universe. This is the verdict of physics. It is impossible for a black hole to last forever. Not because anything is wrong with the black hole, not because gravity is weak or the event horizon is leaky in any conventional sense, but because quantum mechanics and thermodynamics are laws, and laws do not bend, not even for the most extreme gravitational objects in the universe. The universe demands consistency. It demands that entropy be accounted for, that energy be conserved, that information not be destroyed, and in satisfying these demands, it has decreed that black holes, too, must have their endings. What a strange and magnificent universe it is, in which even the most fearsome and total prisons that physics allows are, in the end, temporary, in which the darkness is not permanent, in which even the event horizon, the ultimate boundary, ultimately yields, not to force, not to any escape velocity, but to the relentless and patient logic of quantum mechanics and thermodynamics, working together across timescales that make the history of the universe to date look like an opening moment. Stephen Hawking, working through the mathematics in 1974, discovered something that no telescope could have shown us, something that will not be directly confirmed for timescales unimaginably beyond the current age of the universe. He discovered that the darkness of a black hole is not eternal, that even in the most extreme corner of space-time, the laws of physics insist on consistency, on balance, on the flow of entropy. It was a gift of pure thought to human understanding, and its implications continue to reverberate through physics 50 years later. And so we arrive at the conclusion that has been building throughout this long journey through gravity, quantum mechanics, thermodynamics, and space-time. It is impossible for a black hole to last forever because the universe will not allow it. the same laws that allow black holes to form. The laws of general relativity and gravity, when combined with the laws of quantum mechanics and thermodynamics, guarantee their eventual dissolution. This is not a contradiction, but a deep consistency. The universe is governed by laws, and those laws taken together tell a complete story. A story that begins with the Big Bang and ends with the cold, quiet afterglow of the last evaporating black hole, its final flash of gamma rays marking the end of the last great structure in the universe, the dispersal of the last concentrated pocket of energy and information into the universal sea of maximum entropy. After that, there is no more change, no more time, in any meaningful sense, just the eternal, featureless, unchanging state of maximum entropy. The final silence of a universe that has spent all its complexity, radiated all its order, dissolved all its structures, and arrived at last at the thermodynamic end of all things, a state that will persist, if persist is even the right word, for a duration that makes the evaporation time of the largest black holes seem like an instant. The impossibility of eternal black holes is, in this light, not a sad story, but a profound one. It is the story of a universe that takes its own laws seriously, that does not make exceptions, that counts every joule of energy and every bit of information and every unit of entropy, and that always, always balances its books. In such a universe, nothing lasts forever, not even black holes, and that perhaps is exactly as it should be.